Continuing on with Unit 3, and in this video we're going to talk about learning target 5b, which will be all about graphing polynomial functions. By the end of this lesson, you will be able to create a polynomial equation given the zeros of a polynomial. You will be able to find the zeros of a polynomial and determine their multiplicity. And lastly, we'll look at some gigantic graph examples where we're finding the zeros of the polynomial, their multiplicity, determining the end behavior for that graph, and then using all that information to help sketch a graph. So in learning target 5a and 5b, ultimately we're combining the same concepts together to build up to some of our gigantic examples that we're going to see at the end. We have a couple new concepts to talk about before we can look at graphing any polynomial. So our first concept that we're going to talk about is the factor theorem. So if I have the expression x minus b, if that is a factor of the polynomial p of x, if and only if the value b is a zero of the polynomial p of x, which would mean if I plugged b into all the x's, I would get out 0. That's what makes it a zero of that function. And this is a concept that we've talked about, but we just haven't formalized. So down below in our first example, I've got a chart that we're going to fill in. In the left-hand column is the factored form, so this would be that x minus b expression. And on the right-hand column, we have the zeros, which would be the corresponding b value that comes from the x minus b factor. So if I have x minus 10 as my factor, the corresponding zero is going to be positive 10. And the reason the sign changes is because ultimately what we're doing is we're taking that factor of x minus b and I'm setting it equal to 0, and I'm solving to get x equals b. So by adding the 10 to the other side, that's why I end up with a positive value. Likewise, if I have x plus 4 as my factor, then my corresponding 0 is actually going to be a negative 4, because I would have to subtract that 4 over to the other side if I were to set x plus 4 equal to 0. Now, we've talked about this forward direction before, and we used it in our last section in order to graph. Well, what the factor theorem also tells me is that I get the backwards direction. So if I'm given a 0, so in this case, if I'm given x equals 3 as a 0 of a polynomial, I can find the corresponding factor by subtracting that 0 from x. So then x minus 3 would be my corresponding factor. Likewise, if my 0 is negative 1 for my polynomial, then I would get x minus a negative 1. We can, of course, simplify that down to be x plus 1 as my corresponding factor. And the reason this is going to be helpful, sometimes we're asked to create a polynomial from some given information. So let's look at our first two examples here. In example 2, it says, what is the cubic function in factored form with zeros negative 1, 4, and 7? A couple things to think about here. What does it mean to be a cubic function? So to be a cubic function means that my degree of my polynomial is going to be equal to 3, which corresponds then to why I have 3 zeros here. And I want to eventually write this polynomial in factored form. Well, I'm going to take each one of those zeros and convert them into their corresponding factor. So if we look at the negative 1, 0, the 4, and the 7, why don't we write out what the corresponding factors would be for negative 1, 4, and 7. So for negative 1, the corresponding factor would be x minus a negative 1, or x plus 1. For 4, the corresponding factor would be x minus 4. And for 7, the corresponding factor would be x minus 7. Now that I have all of my factors that go in my polynomial, it's easy to write this cubic function in factored form. I'm going to call it f of x. So f of x is going to be equal to my x plus 1 factor times my x minus 4 factor times that x minus 7 factor. And a couple things I want to talk about. One, I absolutely need to have each one of these factors in parentheses because I'm multiplying these all together. Now there is no need to FOIL this out because the problem asks for it to be in factored form, so in fact I want to leave it as x plus 1 times x minus 4 times x minus 7. If we were asked to put it into standard form, then I'd have to start FOILing it out, and I'd FOIL 2 out at a time and then FOIL the third one into that. The other thing is technically there's more than one correct answer here because I could put any coefficient that I want in front of this x plus 1. So right now I have that invisible 1 as my coefficient, which I could absolutely leave there. Or if I want to make this problem a little fancier, maybe I could pick 5 and put 5 here. I could put a negative number. I could really put any number that I choose as long as I have no x there. So I'm going to leave it as the most basic example here, but we could get more than one correct answer here depending on what we want to make the leading coefficient. Let's look at example 3. So in example 3, it says, what is the quartic function in factored form again, with zeros -5, -2, 3, and 3? Well, what does it mean to be a quartic function? Well, to be a quartic function means that my degree is equal to 4, which lines up with why I have 4 zeros then. So why don't you guys list out all the zeros and then come up with their corresponding factors. So for our zeros, we have -5, -2, and 3. We do have 3 twice, but it's going to create the same factor each time. So for -5 is my 0, my factor would be x minus a -5, which I could simplify as x plus 5. For -2, my corresponding factor would be x minus a -2, which simplifies down to be x plus 2. And for my last 0 of 3, my corresponding factor would be x minus 3. Now, since the 0 comes up twice, when we write this in factored form, I'm going to have an x plus 5 as my first factor, times that x plus 2. But then for the 3 as my 0, since this happens twice, I can write this as x minus 3 times, I need another x minus 3. But there's a way that I can simplify that down a little bit and instead write it as x plus 5 times x plus 2 times x minus 3 squared. And we're going to much rather write these anytime we have multiples of something. We're going to want to group them all together as that x minus our b value to whatever power that is representing however many copies of that factor we have. So since I have 2 copies of x minus 3, that's why I'm writing it as x minus 3 squared. And we're going to prefer this because that actually gives us some information moving forward that we're going to talk about next. And again, if I want to put a coefficient on here, I could pick my favorite number and make that as my coefficient on here. I could even do a negative number. Maybe I'll do like -3 for this one. And so there's technically an infinite amount of answers here that we could have for both problems 2 and 3. But what they all have in common is that they only have these factors as their factors in factored form. It's just the coefficient in front that could change. So let's look at our next new concept, which actually has to do with what we saw in example 3, and that's multiplicity of a 0. So the definition says b is a 0 of multiplicity n in the polynomial p of x means that the factor x minus b appears n times as a factor in that polynomial. So in our prior example up above, since x minus 3 appeared twice, because we had that x minus 3 squared, that's how I knew that this factor appeared twice, was from that exponent, then we say that 3 is a 0 of multiplicity 2. And that might seem kind of silly. Well, I can see it there. There's a 2 on it, so it appears twice. But the multiplicity is actually a very key component when we go to graphing. And depending on the multiplicity, it actually changes the graph. Before we get to the graphing, though, let's just do some practice where we're given a polynomial and we want to determine the zeros and then find their multiplicity. So in example 4, we have f of x equals x minus 2 times x minus 1 squared times x plus 6 cubed. And I have a little chart here, and we're going to start to see this chart through a lot of examples where we have the factors in the first column, the zeros, and then the multiplicity. I didn't want to make it a full chart filled in because it's really our job to figure out how many factors do we have, then what are their zeros and what are their multiplicity. So when I look at this polynomial, the factor is each unique piece here that involves an x. So I see 3 of them that I have. I have the x minus 2, I have the x minus 1, and lastly, I have that x plus 6. And I want to point out something. I am not taking the exponents at all when I list my factors, because the exponents actually have nothing to do with what the factor is. That's where the multiplicity comes into play. So for the factors, we're just listing each unique factor that we have. X minus 2, x minus 1, x plus 6. Now from here, we want to find the corresponding zeros. Well, this is what we did in both Learning Target 5A as well as earlier up in the video. If x minus 2 is a factor, then that means that positive 2 is the 0. And remember that comes from if I set the factor equal to 0 and solve for x. Likewise, if x minus 1 is a factor, then 1 is a 0. And lastly, if x plus 6 is a factor, then that means that negative 6 is a 0 then of this polynomial. Now that we have the factors and the zeros listed, we can determine their multiplicity. And the multiplicity is coming from the power listed on each factor. So on the x minus 2, there is no power listed. There's technically that invisible 1 there. So x minus 2, that factor, has a multiplicity of 1. Now for the x minus 1, since that appears twice, that means that the 0 of 1 has a multiplicity of 2, since that's the power on the x minus 1 factor. And for our last factor of x plus 6, since we have a power of 3 on there, that means that negative 6 as a 0 has a multiplicity of 3, since its corresponding factor appears 3 times in our polynomial. Let's look at one more example of where we're just identifying the factors, finding the zeros, and their multiplicity. So in example 5, we have g of x equals x to the 5th times x minus 3 times x plus 4 to the 4th times x minus 8 to the 7th. Why don't you guys pause the video and list the factors and their corresponding zeros, and then we'll check that together. So for my factors, I think I have 4 unique factors on this one. I have x minus 3, I have x plus 4, and then I have that x minus 8. So each one of those is a unique factor here. And we hadn't actually seen this factor of x yet. This is new here, but I know that it's a factor because there's a variable in it. Versus if there was just a number in front of it, like we saw up in the prior 2 examples, then that wouldn't be considered a factor. But since there's an x, I do get that factor of just that x by itself. Now to find the corresponding zeros, remember we're setting the factor equal to 0 and solving for x. Well, if I set x equal to 0 and I solve for x, it already is solved, and so that tells me that my corresponding 0 is 0. Alternatively, another way to think about this is x is the same thing as x minus 0, so that's why 0 is our corresponding 0 for the factor of x. Now for the factor of x minus 3, the corresponding 0 is going to be positive 3. For x plus 4, the corresponding 0 is negative 4. And then for x minus 8, the corresponding 0 is positive 8. So again, for every single unique factor, I have to be listing it in my factor column, and every factor has its own unique 0 that comes from it. So I can, once I have the factors identified, I can identify the zeros. And again, in the factor column, I'm never listing any of the exponents up there. That's what the multiplicity is for. Why don't you guys pause the video now and find the multiplicities for each one of these zeros. So for our first 0 of x equals 0, our multiplicity on that guy would be 5, since that is the exponent on that corresponding factor. For our next 0 of x equals 3, our corresponding multiplicity would be 1, since I have that invisible 1 as my power. For the negative 4, the multiplicity there would be positive 4, since that's the power that we have on the corresponding factor. And for our last 0 of 8, our multiplicity then would be 7, since that is the corresponding power for that factor. Now, identifying the factors, the zeros, and their multiplicity is going to be extremely important as we go to graph. And the reason that happens is the multiplicity actually affects the graph. So if b is a 0 of multiplicity n, then I have 2 options. The first case happens if n is odd. If the multiplicity here, so n is our multiplicity, if our multiplicity is an odd number, then the graph is going to cross at that 0. So on this first picture up here with the blue line here, we have a graph that's crossing through the x-axis, since the graph goes from below to above. It could also come from above to below, but it actually crosses through that x-axis. Versus if I have a multiplicity where n is even, then my graph is going to, what we say, bounce at that x-intercept. So on our bottom graph here, we can see this graph is bouncing at our x-intercept since the graph goes up, touches and then turns back around and stays on the same side of the x-axis. So crosses is what happens when we go through the x-axis, and bounces is what happens when we touch the graph and then come back the same direction we came from. So we stay either completely below, or if we were to bounce from the top of a graph, we would stay completely above the x-axis. So both of these are cases where we say the graph bounces versus crosses. So if our multiplicity is odd, then we cross at that x-intercept, and if our multiplicity is even, then we bounce at that x-intercept. And we're going to now use all of this information to combine into a gigantic example where we graph a polynomial. So let's look at example 6 here. We're going to consider the polynomial p of x, which is x to the fourth plus 2x cubed minus 8x squared. And we have quite a bit of information to find here. And in part A, it says to fill the following chart in to determine the factors, the zeros, their multiplicity, and the behavior at each zero. Well, the first thing I need is the factors. And right now, p of x is not in factored form, it's in standard form. So my first job here then is to actually factor this polynomial. So when I look at x to the fourth plus 2x cubed minus 8x squared, I'm first looking to see if I have a greatest common factor. Is there a greatest common factor for p of x? So there is a greatest common factor for p of x. Each one of these terms has an x squared that I could factor out of the whole polynomial, and that would leave me with an x squared on the outside, and then inside I'd be left with an x squared minus a 2x, whoops, not minus, so we'd have plus, there we go, a 2x, and then minus that 8 for our constant term. And so that happened because we factored out an x squared out of each one of our original terms. Now from here I can continue to factor this, and I can factor the x squared plus 2x minus 8. Why don't you guys pause the video and factor x squared plus 2x minus 8, and if you need so, feel free to use an X Games to think about how that factors. So to factor our quadratic now that's left over, oops, there we go. So to factor our quadratic that's left over, I'm looking for two numbers that multiply to be negative 8. So to factor our leftover quadratic, we're looking for two numbers that multiply to be negative 8 and add up to be positive 2. The two numbers that are going to work is going to be positive 4 and negative 2. So that tells me I get the factors of x plus 4 as well as x minus 2. So we're using a lot of skills from our last unit, not only with factoring right now, but we are going to also bring back the quadratic formula in some later sections to come in this unit. Now we can actually start filling in our chart in part A. So our factors, I have the x plus 4, and the x minus 2 as my three unique factors. So I can list those factors right here. Now that I have the three factors, why don't you guys pause the video and list the corresponding zeros. So for the corresponding zeros, for the factor of x, my corresponding zero is just 0. For the factor of x plus 4, my corresponding zero is going to be negative 4. And for our last factor of x minus 2, our corresponding zero is going to be positive 2. And remember, we're getting all of those by setting the factor equal to 0 and then solving for x from there. Now we need to find our multiplicities. Why don't you guys pause the video and find the multiplicities for each one of these zeros. So our multiplicities, remember, are coming from our powers, or our exponents in factored form. Since the factor x appears twice, since I have that x squared, the multiplicity then for this 0 would be 2. For the x plus 4 factor, that only appears once, so that means the multiplicity for negative 4 is going to be 1. And the x minus 2 factor also only appears once, so the multiplicity for the 0 of x equals 2 would also be 1. And we had done that back in some prior examples. Now the behavior is what happens at each of these zeros. And this goes back to, does the graph cross or does the graph bounce there? So why don't you guys pause the video and go back and read your notes and determine if the multiplicity is odd, what will happen? And if the multiplicity is even, what will happen on the graph? So if the multiplicity is odd, the graph is going to cross there. And so 2 is an even number, so it's not going to cross there. But 1 and 1, since they're the same number, are both odd. And that tells me that my behavior on my graph is going to cross at both of those x-intercepts, since my multiplicity is odd. Now for the multiplicity of 2, since that 2 is an even number, then it tells me my behavior on the graph is that that x-intercept is going to bounce. Now the next step we saw similar questions in our last video as well. We want to find the x-intercepts. Well, remember our x-intercepts are just the coordinate pairs that correspond to our zeros. So I have 0, 0, then we get -4, 0, and then we have 2, 0. For our y-intercept, remember to solve that we're going to set x equal to 0, and we can use either standard form or the factored form. So if I sub in 0 for x, I'm finding p of 0. If I use the original form, the standard form that was given, I'm subbing a 0 in for all of those x's, so I get 0 to the 4th plus 2 times 0 cubed minus 8 times 0 squared, and all of that is just going to zero out and leave me with 0 then. So my y-intercept then is going to be 0, 0. And we saw an example like this in the last video, and if 0, 0 is an x-intercept, I automatically knew that 0, 0 was the y-intercept, since that's the one place on a graph that's both an x and a y-intercept, and that's only possible to have one y-intercept on a graph of a polynomial, since they are functions. Now the last thing we need to determine before we can graph is the end behavior. So the end behavior we learned about in Learning Target 5A, and that is based off of the leading coefficient and the degree. So I'm going to use LC for leading coefficient. Our leading coefficient I can get from standard form, and that would be the 1 that's in front of the x to the 4th. My degree is our highest power of our polynomial, which would be 4 in this case. And since my leading coefficient is a positive number and my degree is even, I can now determine my end behavior. Why don't you guys pause the video, and if needed, look back in your Learning Target 5A notes and determine what the end behavior will be if I have a positive leading coefficient and an even degree. So for my end behavior is going to be up, and we are asked to justify that, and that happens just because our degree is even and our leading coefficient is positive. This is similar to remember that y equals x squared graph, since I have an even degree and a positive leading coefficient. Now that we have all this information, we can actually use that to sketch a graph. So remember, on our graphs, I'm not going to give you guys graph paper, and I would suggest not using graph paper at all, because you want to space this graph out as much as you possibly can. So instead, I'm starting with just an x and a y axis that's blank, and it's my job to label that graph. So I'm going to start by graphing my x-intercepts. So I have 0, 0, so that's easy to plot. I have -4, 0, so I'm going to go to the left -4, and I'm making these spaces super big because I want enough space in between my x-intercepts to really be able to graph it easily. Then my last x-intercept is at 2, 0, so I'll go 2 to the right. My y-intercept is already plotted since it was also an x-intercept. So I only have to have these 3 points exact on the graph. Remember, we are sketching this, so your graph is going to look slightly different than mine. I'm only worried about the x and the y-intercepts being the exact points. From here, we're going to use the end behavior. So up and up means that from the far left side, the graph goes up, and from the far right side, the graph goes up. So from my leftmost x-intercept, which is the -4, the graph is going to go up from there. And from my rightmost x-intercept, which is at +2, the graph is also going to go up from there. So that is that end behavior of up and up. Now we have to figure out what's happening inside. And before, I just had us cross, cross, and cross. Well, I could only do that because each one of our factors had a multiplicity of 1. So because that multiplicity was odd in our last video, that's why we crossed at every single point on our graph. Now that we actually have this behavior, we have to focus back and see, well, what's actually happening at each one of these x-intercepts. So I'm going to start from left to right on the graph. And at -4, let's see what's happening. So if I go back to my table up above in part A, when I have the 0 of -4, the multiplicity was odd, so we cross there, which means at -4 I'm going to cross through this graph. Then I do have to connect down to my next x-intercept, which is at 0, so I know that I have to make that connection. And we talked about last time how this could maybe dip way down and come up. I can make it shallow. You really get the choice here. I'll keep that kind of larger dip there. Oops. So I'll have this dip all the way down and then come back. So this is where we're crossing at this x-intercept because I knew that from my multiplicity. Now at 0, I have to pay attention to what's going on. So when I have the 0 at 0, I have a multiplicity of 2, which is an even number, so that means that the graph bounces here. So I don't get to cross through, I wouldn't keep going here. Instead, my graph is going to bounce back in the direction it came. Not the exact direction, but the same side of the x-axis. So since I'm coming up from below, the graph turns around and bounces like that. And so this is what we would call a bounce. Oops. A bounce on that graph there. And now I know it needs to connect to my next x-intercept, so it does have to turn back around and go to +2. And at +2 here, it's going to end up crossing then because I already had my end behavior, but I want to make sure that that matches up with what I found above. So these problems are really self-checking because of all the information that goes into play. There's only one unique way to connect these all together. And so since it bounced at 0, then it turns back around and stays underneath the x-axis, and it goes back to the next x-intercept. And at my next x-intercept of +2, since the multiplicity was 1, which is odd, the graph is crossing there, which matches up with what I have already from connecting from the prior x-intercept and then connecting the end behavior from there. Now, of course, labeling cross, bounce, cross, we're not going to actually label these on our graph, but I want you guys to be able to see what it means to cross versus bounce on a graph. And so using all this information about the factors, the zeros, the multiplicity, we can then determine the behavior at each x-intercept. We can find the x-intercepts, the y-intercepts, determine the end behavior just like we did in our last video, then put all that information together to graph it. And this is what I'm calling one of our gigantic examples here, since there's so much that goes into play to getting one of these graphs. Let's look at another example. So in example 7, we have the polynomial p of x equals -2 times x plus 1 squared times x plus 3 times x minus 2 cubed. Now the nice thing about example 7 is we're already in factored form. So p of x is already in factored form for us, so we can jump right into part A. So we want to fill in the factors, then determine the zeros, the multiplicity, and the behavior. Why don't you guys pause the video right here and list all the unique factors for this polynomial in example 7. So in example 7, I see 3 factors, the x plus 1, the x plus 3, and that x minus 2. So I have x plus 1, x plus 3, and x minus 2. Now the reason the -2 in front is not a factor is because there's no x there. That's just going to be a coefficient, which is actually going to end up being our leading coefficient for our polynomial, but it is not a factor since there is no x there. So we just have x plus 1, x plus 3, and x minus 2. Now to find the corresponding zeros, why don't you guys pause the video and list those out. So for our corresponding zeros, for x plus 1, -1 will be our 0. For x plus 3, -3 will be our 0. And for x minus 2, +2 will be our 0. Why don't you guys pause the video and list out the multiplicities for each one of those zeros. Now the multiplicity comes from the power, or that exponent on the factor. So for the x plus 1, I have an exponent of 2. So that means that -1 has a multiplicity of 2. For the x plus 3, I don't have any power up there. That's that invisible 1. So -3 has a multiplicity of 1 then. And for the x minus 2, I have a power of 3 on there, which means for the 0 of x equals 2, I have a multiplicity of 3. Now to determine the behavior, that depends on if the multiplicity is even or odd. Why don't you guys pause the video and determine the behavior at each one of these zeros. So since for our first 0 here of -1, since I have a multiplicity of 2, which is even, that tells me that I'm going to bounce on the graph at that x-intercept. For -3, the multiplicity is 1, which is an odd number, which means we're going to cross then. For the 0 of +2, my multiplicity is 3, which is also an odd number, so I'm also going to cross at that point then. Now for my part B of my x-intercepts, I have no new work that I need to do. I can get all of my x-intercepts from the zeros that I found above. Why don't you guys pause the video and list out your x-intercepts. So our x-intercepts here are going to be -1, 0, -3, 0, and 2, 0. And that's coming from each one of those zeros in part A. Now to find our y-intercept, we are going to have to do some more work this time, but we can find our y-intercept by setting x equal to 0. Why don't you guys pause the video and find your y-intercept. So to check that, we're looking for what p of 0 is equal to. So if I sub in 0 for each one of the x's, I get -2 times 0 plus 1 squared times 0 plus 3 times that 0 minus 2 cubed. Simplifying this out, we get -2, well 1 squared is just 1, 0 plus 3 is 3, so I get -2 times 1 times 3, and then -2 cubed is actually going to give me a -8, because I'll have that negative times another negative. And if we multiply all of those out, I'm going to end up with a positive 48, which means my y-intercept is going to be at 0, 48 then. The last piece of information I need before I can graph is going to be the end behavior. And remember, the end behavior comes from our leading term. So if we're going to find our leading term, we don't have standard form, but I don't need to get completely to standard form. I just have to factor out what all of my highest powers are. So let's look back at our factored form. That -2 is going to end up being our leading coefficient, and then I would multiply out the x, and the x. But what I have to worry about now is all of these exponents on here. So there's actually a shortcut that we can use to find our leading term. Now the leading coefficient is coming from any numbers in front, which would be the -2. And my job is to just figure out, well, what would be our exponent on that x? Well, if I look at this, I technically have an x squared, then I have a single x, so that's 3 total, and then I have an x cubed, so if I have 3 more, I have a total of x to the 6. Another way to see this is if I add up my multiplicities. So if I take all my multiplicities of 2 plus 1 plus 3 from part A, if I add those up, that actually gives you our degree. And so that's another way that I can check that my degree here would be in 6, so I would end up with a -2x to the 6 as my leading term. Using that information, the fact that we know that our degree is equal to 6, and our leading coefficient is equal to -2, why don't you guys pause the video and determine the end behavior. So in this case, I have an even degree, and I have a negative leading coefficient, so my end behavior is going to be down, and then down, and that happens because my degree is even, and my leading coefficient is negative. And remember, we are asked to justify, so we have to explain our answer there. Now we can use all this information to sketch a graph. And I want to reinforce the fact that this is self-checking. There is only one unique way to have all of this information line up from here. And we're going to start by just plotting the for sure points on our graph. So I'm going to plot our x-intercepts at -1, 0. So I'm going to plot that guy there. Remember, we want to space this out as much as possible. It's also our job to put tick marks on the graph, so I have to have these tick marks that are counting. I also have -3, so -1, -2, -3. Put that point. And then I also have +2. So then I'll go 2 to the right. Those are my x-intercepts. Now my y-intercept is up there at +48. And I'm not going to do 48 tick marks. That's kind of a little ridiculous. 48 is a large number. So instead I'm just going to put it way up here on my x-axis. I'm going to put a dot, but I'm also going to label it so that I know, oops, that that is at 48. Let me make that for sure look like an 8 then. And so since I'm not putting all the tick marks up there, that's fine, but I need to label the number so that I know where it's at. And if I didn't label it, I would just assume that that was 1 unit up. So we have to make sure we're labeling our graph. There is no need to do 48 tick marks. That seems rather crazy and a little ridiculous. So instead we'll just be labeling where our y-intercept is at. From here, now that we have all the points on our graph, we can use the end behavior next. So our end behavior is down and down, which means to the far left we go down and to the far right side we go down as well. So why don't you guys pause the video and add in that end behavior for us, and then we'll check it together. So since my end behavior is down and down, then to the far leftmost x-intercept, which is at -3, this graph is going to go down from there. And from the far rightmost x-intercept, which would be +2, the graph is going to go down from there as well. Now my job is to play connect the dots, and the last thing we have to worry about is the behavior on the graph. And we're just going to work from the left to the right side of this graph. So let's start with our leftmost endpoint of -3. So at -3, I'm looking at this middle spot here from part A. So when I have a 0 of -3, the multiplicity is 1, which is an odd number, so the graph is crossing there, which means I get to go up and through that x-intercept then, and that's where I'm crossing. Now from here, my next x-intercept or my next point on my graph would be at -1, so I have to reach that guy, so I'll come down and touch that from there. And at -1, if I go up to part A and use this chart, at -1, I had a multiplicity of 2, which is even, so I have to bounce. So although I'm touching here at -1, I'm going to bounce and turn back around, which is the only option that can happen here. Since I cross through at -3, the next point I go to is at -1, but from there I have to reach +48. So from there I have to go up to get back up to 48 then. So it would only make sense that at this x-intercept of -1, we are bouncing on this graph. Now if we keep going through here, now when I reach a y-intercept, I always just go through that. There is no crossing or bouncing here. Because I need to have a function, my graph has to keep going to the right. So I'm going through that y-intercept, and I'm coming down to my next x-intercept, which is at 2. And based off of connecting from the y-intercept to the x-intercept and then using the end behavior, it's crossing here. But let's make sure that that lines up with what we found up above. And when we had that 0 of 2, our multiplicity was 3, which is an odd number, so yes, indeed, we are crossing. So each one of these does match up with this graph down below. And that would be our final answer of our graph here. So we can see from all of these pieces of information, they compile together and they create this nice perfect sketch of our graph. And there is only one way to connect these together. So if you're starting to connect stuff, and for instance, let's say maybe at -1, I thought the graph was supposed to cross, and I'm going to draw it in red here because this is not what is part of this graph. Let's say I accidentally thought that an even multiplicity crosses. So I thought, oh, I have to cross here. Well, my next point is up here at 48, so to go back up to it, I would have to cross the x-axis again, which is a huge issue because that's creating another x-intercept. But I don't have another x-intercept, which is why we start always by plotting those x-intercepts. So that's one way to check your work. So if you have something that would cross through, but then you can't connect back to the next point, go back up and see what information went wrong. Something was wrong there. Maybe our end behavior, maybe a prior x-intercept we had incorrect, or we had the wrong behavior there. We can use all of this pieces of information to self-check. And when I'm going through these, I always want to make sure I'm connecting from left to right. My graph is still a function, so it passes the vertical line test, and I only have the amount of x-intercepts that I already found back in part B. Now there's one more example that's in your notes. It's example 8 that I'm going to scroll down to here. I want you guys to try example 8 completely on your own, and then we're going to use this as a warm-up and check this together at the start of class tomorrow.